Hi, this is Dr. O'Connor. In this video, I'm going to talk about stereochemistry and chiral molecules. So our main goal here will be to identify a chiral molecule. But first, we have to start with some terms. So what is stereochemistry? It is the study of the relative three-dimensional spatial arrangement of the atoms in a molecule. We've already talked about constitutional isomers, and we know that constitutional isomers have the same molecular formula, but they differ in how the atoms are arranged. Stereoisomers, on the other hand, have the same molecular and structural formulas, but they differ in the spatial arrangements of their atoms. So they basically differ in the arrangement of the bonds in three-dimensional space. Same connection of atoms, same molecular formula. And then we talk about configurations. And these are stereoisomers that cannot be converted into one another by rotation around a single bond. Let's take a look at an explanation of what chiral means, because this is what's going to apply to molecules. Now, we know that the mirror image of our left hand is the right hand, and vice versa. I cannot superimpose the mirror images of my hand on each other. In other words, one is not going to completely fit on the other. So if here I have a hand, here I have the mirror image. If I rotate this mirror image, I cannot superimpose it on my hand. So objects that have handedness are said to be chiral. Okay? So not all objects are chiral. We don't have a left-handed basketball or a left-handed coffee mug or a left-handed chair. So objects like a chair, for example, that lack this handedness are said to be non-chiral or achiral. What that means is the mirror images are superimposable, and the reason why is because there is a plane of symmetry. And the same thing occurs with molecules, which I'll explain in a moment. Think about your feet, right? You have a right foot and a left foot. So your left shoe is not going to fit on your right foot, and your right shoe will not fit on your left foot. And that's because both are chiral. Your feet and the shoes are chiral. So in order for a molecule to be achiral or not chiral, what is needed is a plane of symmetry. So we notice here with the chair, we can draw a plane, and the left side is the same as the right side. Let's take a look at the letter M. The letter M, this is achiral because its mirror image is exactly the same. The two mirror images can be superimposed. However, if I write the letter F, and go ahead and do this. Take a piece of paper and write these letters, and then take a look at the mirror image. And you'll see the mirror image of the letter F is different. And if I rotate the mirror image, I cannot superimpose it on this here. In other words, there's a difference in the right and the left, just like in your hand. And there is no plane of symmetry. Here in the M, we have a plane of symmetry. The chair, we have a plane of symmetry. Now, let's talk about molecules. This is a little different. So let's take a look at this molecule here. We have a central carbon, and we see that that central carbon has 4 bonds. But we see that 2 of the groups are identical. So in other words, there is 1, 2 hydrogen atoms. So there's a plane of symmetry here. In other words, this plane, you could think of it as a mirror. Okay, so the mirror image of this is going to be superimposable. So we can superimpose the mirror images of this molecule. Now, let's take a look at this molecule here. Notice that the carbon is bonded to 4 different groups: a chlorine, an iodine, a hydrogen, and this methyl group. Now, there is not a plane of symmetry here. In other words, one half of this molecule does not reflect the other half. And this, one half of the molecule does reflect the other half, but not here. We say that this carbon here is chiral. So let's define a chiral carbon. So a chiral carbon atom, or a chiral center, is a carbon atom that is both tetrahedral, so you have to have a tetrahedral geometry, and has 4 different groups attached to it. One half does not reflect the other for a chiral molecule. So again, what we have to have is a chiral carbon atom. We also call these chiral centers. We call them asymmetric centers. Okay, so a chiral center is a carbon atom that has a tetrahedral geometry and has 4 different groups attached to it. For this molecule here, let's say I have this here, and this. So what I do is I look at each carbon. This carbon here, it has 3 identical groups, 3 hydrogens. So this is not chiral. This carbon here has the methyl group, a hydrogen, a chlorine, and this ethyl group. This is a chiral carbon. I indicate a chiral carbon with an asterisk. Okay, and then let's take a look at this carbon. This carbon is bonded to 2 hydrogens. So right there we know it's not chiral. But this molecule is chiral. So the 2 mirror images could not be superimposed on one another. Remember, in order to have an achiral molecule, we have to have a plane of symmetry. And in this case here, when we have a carbon bonded to 4 different groups, there is no plane of symmetry. Let's look at the alcohol 2-butanol. It is a chiral molecule. And we can see that this carbon, the carbon number 2, is bonded to a methyl group, a hydroxyl group, an ethyl group, and a hydrogen. They're all different. So this is chiral. I would indicate the chiral carbon by putting an asterisk near that carbon. And here we can see a representation of the mirror images. Again, we can't, if I were to rotate this one, I cannot superimpose it on this one. So the mirror images are not superimposable. Let's take a look at butane. Butane, well, this carbon here is not chiral. This carbon here is not chiral. It's bonded to 2 hydrogens. And the central carbon is not chiral. It's bonded to 2 hydrogens. So there's no chiral center in this molecule. Therefore, butane is an achiral molecule. So the mirror images of butane are superimposed. What we have is a plane of symmetry. So let's talk a little bit about this, and then we'll work on identifying more chiral centers. And this is very important when we get into biochemistry. We have to be able to determine these types of isomers. The 2 mirror image forms of a chiral molecule are called enantiomers. These 2 mirror image forms are called enantiomers. So, for example, there are 2 enantiomers for butanol. We also call enantiomers optical isomers, and that's because of the way they affect polarized light. And we'll talk about that much later. Enantiomers are one type of stereoisomer. A pair of enantiomers may have many of the same physical properties. So they have the same melting points, same solubilities, same isoelectric points, same density, same physical properties. The only way they differ is how they affect polarized light. One enantiomer will rotate the polarized light to the right, and we call that the D, or we give it this plus sign in parentheses. This is dextrorotatory, and we'll talk about that later. And the other other enantiomer will rotate the light to the left, and this is called the L, or we have this minus symbol in parentheses. So that'd be the L or levorotatory enantiomer. Now, pairs of enantiomers have the same physical properties as we just said, but the one thing they differ in, besides how they affect polarized light, is their biological activity, odors and tastes. So this is why it's important in biochemistry that we are able to identify enantiomers. So for example, we have this molecule here, which is called carvone. But there's a chiral center. So one chiral center. So this can exist as L-carvone or D-carvone. And right here is the chiral center, this carbon here. It's bonded to 2 or 4 different groups. They differ in the taste and odor. L-carvone, that's in spearmint. Spearmint has a minty flavor. And D-carvone is responsible for the flavor of caraway seeds. We find caraway seeds usually in rye bread, in seeded rye bread. So 2 very different tastes and odors. What's going to be important to us when we get into the biochemistry is how pairs of enantiomers differ in their activity as drugs. So, for example, we have this molecule here, and the L form is used to treat tuberculosis. However, the D form will cause blindness. So that means that when this drug is synthesized, that this D form better be separated from that drug mixture. Okay, years ago, it was very difficult to separate enantiomers. And nowadays, we have better technology and we're able to separate enantiomers. Many drugs consist of enantiomers and they're not separated, and that's because the inactive one is not going to cause any harm. But back in the 60s, there was a drug called thalidomide, and it was given to pregnant women for morning sickness. And it worked very well. The only problem is its enantiomer caused a lot of birth defects, and there were a lot of babies born with some terrible birth defects. We talk about there being so many compounds in organic chemistry, and we talked about constitutional isomers, but now we also have to be concerned with these stereoisomers, these enantiomers. And there are other types of stereoisomers too that we'll talk about later. Anyway, let's go ahead and identify these chiral carbons. Let's take a look at this here. We have 1, 2, 3, 4, 5. So that's a pentane. And what we have is 3 chloropentane. So my question is, are any of the carbons chiral here? Now, some of you might have a hard time working with the line structure, and that's fine. So what we can do is we can convert this line structure into a structure, into a structural formula like so. And okay, so these are hydrogens. Okay, so we have all these hydrogens here. So let's go ahead and see if this molecule, this 3-chloropentane, has a chiral center. Well, this first carbon we know is not chiral. It's bonded to 3 hydrogens, so that's not chiral. The second carbon is not chiral, 2 hydrogens. The third carbon, let's see, it's bonded to a chlorine, it's bonded to a hydrogen, but here we have an ethyl group, and here we have an ethyl group, so that's not chiral. We know that carbon number 4 here is not chiral. It has 2 hydrogens. Carbon number 5 is not chiral. So this is an achiral molecule. But let's take a look at this one. Let's do this one. This here is 2. Oops, I forgot to put the chlorine here. 2-chloral pentane. And again, what you can do is you can draw out the structure. I'm not going to put the hydrogens in, just remember the hydrogens are there. And let's go ahead then and look at carbon number 1. It is not chiral. It has 3 hydrogens. Carbon number 2. What we have is a chlorine. We have a hydrogen. We have this methyl group, and we have an ethyl group. Looks like carbon number 2 is chiral. Carbon number 3 is not chiral. Carbon number 4 is not chiral, and carbon number 5 is not chiral. So our chiral center here is carbon number 2. So this is a chiral molecule. So again, all you're doing is you just want to make sure the carbon has 4 different groups. Let's take a look at this molecule here. And let me do this and this one here. This happens to be lactic acid. You wouldn't know that yet. We'll study that a little bit later. So again, if I'm not comfortable with the line structure, so I know that this here is a CH3. And next to it, I have a carbon that has a hydrogen and the OH group. This carbon has a double bond, and it's bonded to this OH group. So let's take a look at this and see if lactic acid is a chiral molecule. So this first carbon, no, it's bonded to 3 hydrogens. Let's look at this second carbon. It has a hydrogen. It's bonded to an OH. It's bonded to this group here and this methyl group. So this carbon is chiral. Let's take a look. Is this carbon here chiral? No, it can't be, because why not? It doesn't have a tetrahedral geometry. It has a trigonal planar geometry. So that could not be chiral. It doesn't have 4 groups. It has 1, 2, 3. Done some of these. Let's take a look back here at, I want to go back a slide. Oh, let's see. We'll go down here. Here's what I wanted to look at. I wanted to look at this carbone. And we said this molecule had a chiral center, and it was this carbon. You're like, okay, well, I see here's one group, okay, that's bonded to this carbon. Here's another group, but what about this ring? Here's what we do. We go ahead and trace a path around the ring one way, and then trace a path around going the other way. If both are equivalent, then we wouldn't have a chiral center. But in this case, look what happens. Let me get my green here. Okay, so I start here at the chiral center. There's carbon 1. Carbon 2 has this double bond. Well, we'll call that carbon 1 at the center. So carbon 1, carbon 2, carbon 3 with a double bond. Here we have a methyl group. Here's that double bond. Here's the other carbon, and this way. Now, if I trace the path, get a different color, this way, it's very different, okay? I don't get to my double bond until 1, 2, 3, 4. Here, when I go around this way, it's 1, 2. You trace the path around. Both paths were not identical, so this would be the chiral carbon. So let's look at some simple ones. So we've seen when we have simple compounds that don't contain rings, it's easy to identify a chiral carbon. But when we have rings, it's a little bit different. So let's go ahead and take a look at this, and I'll put a Cl here. So I'm interested in this carbon right here. Is this a chiral carbon? Well, we got to remember that these carbons are bonded to 2 hydrogens, okay? And there's a hydrogen here. So we're taking a look at this carbon. It's bonded to a chlorine, a hydrogen. Now what I'm going to do is I'm going to trace my way around the ring. When I go this way, it is identical to when I go this way. So this would not be chiral. This is achiral. Now how about this one? We'll put a Cl here, and we'll put a Cl here, okay? So again, we have to keep in mind that we have these hydrogens. Oh boy. Okay. We have these hydrogens. Each of these has 2 hydrogens, right? 2 hydrogens. Now what I'm going to do is I'm going to trace. I'm going to start with this carbon here. So we'll start here. I'm going to trace around, and I go here, and I come across this Cl, okay? But it's 2, 3, 4, 5, 6. So now let's go around the ring the opposite direction. So I'm going to start again at this carbon. Oh, I hit the carbon Cl bond, right? It's adjacent. That carbon Cl bond is adjacent to that carbon. So when I trace around the ring, both directions are not equivalent. So this then is a chiral carbon. Let's do the same with this chlorine. So let me get rid of some of this here. Okay, so now we'll go with this carbon here. So I'm going to go ahead and I'll go ahead and trace around the ring going this way. Okay, and it is different from when I trace going this way, because I come to this carbon chlorine, right? It's adjacent. When I go this way, there is no carbon chlorine that's adjacent. So this would also be a chiral carbon. So I have 2 chiral carbons in this ring. Now, how about this one here? Wait a minute. Let's take a look at this one. There are other ways to do this, but I find that tracing a path around the ring from the chiral carbon going both ways is the easiest way to do it. I think some of you see right away, oh, there's symmetry here. There would be a plane of symmetry here. Here there is no symmetry, okay? But some of you can already see that, I know. So we'll start with this carbon here, and we'll go ahead and trace around the ring. So let's see. So 1, 2, 3, 4. There's my carbon Cl, 4. Keep going around the ring back to 1. Now I'll trace around the ring the other way. So we'll go to 1, 2, 3, 4. So both times when I trace a path around the ring going one direction, in the 4th position I have a chlorine. When I go in the other direction, in the 4th position I have a chlorine. This is not a chiral carbon. And you can see the same thing's going to happen on this side. I can go around the ring this way. On this 4th position, it's a 1,4 position, right? Is a chlorine. When I go around this way, again, the 4th position, or that 1/4 position, is a chlorine. So this is an achiral molecule. It is not chiral. So I just wanted to give you an idea of how to do the rings, because you're going to see a lot of chiral compounds that have rings, and you're going to think, well, how in the world do I determine if this is chiral or non-chiral? Again, it can get more complicated than this, but we're not going to go there in our GOB chemistry course. So everybody have a nice day, and thanks for watching.